Thank you for the introduction. I represent JSR, RD at Technology and Digital Transformation Center, Digital Deputy General Manager, Yuya Ohnishi. So the quantum computer, 4 years experience in the chemical enterprise. So I was involved in the quantum computing for 4 years. So as I read the title, after I sent the material, I realized I was involved in the quantum computing 6 years, not 4 years. Therefore, let me correct my title. 6 years, so 2018, 2019, on 2 occasions, I visited the West Coast, the Q2B. So this is the first time that the venue has been moved to let the Japanese participants in the Q2B. So I'd like to start by the special thanks to Cambridge Quantum, IBM, Keio University, Mitsubishi Chemical, Osaka University, QNASUS, University of Tokyo, and my colleagues at JSR. I'd like to express deepest appreciation for their collaboration and support. Without their support, I was not able to stand at this podium to make this presentation. So let me reiterate my thanks to all of you. So who are we? What is JSR? Corporate philosophy is materials innovation, precisely designed and synthesized material to be applied to leading-edge industry society to create value, enhance value. That is the principal enterprise philosophy. This organization started out with the manufacturing rubber material for the automotive tire. So the polymer technology we have developed through the tire production has been applied to more diverse areas. Major business areas broadly classified, there are 3 areas: digital solution business, life science business, and plastic business. So those are 3 domains of our business. As I mentioned, historically, our business began with the elastomer business, that is the rubber making for the automotive tire. However, this was sold to ENEOS this past April. So those are 3 major business domains that we do operate in. So out of those 3, digital solution business is the area that the JSR is involved in the quantum computing. So let me focus upon the digital solution business because this has triggered JSR to be involved in the quantum computing. Digital solution business could be further broken down into further 3 subcategories. The first one is semiconductor material. We are not talking about silicon or metal oxide. That we are not talking about the semiconductor per se, but we primarily they develop and manufacture the material that is utilized for the semiconductor devices for the CPUs and memories. For instance, the primary material we are engaged in photoresist. Photoresist is the material that is required for cause reaction against the light, or optical reaction to create circuits upon the semiconductor devices. Display material, for instance, the LCD display you're familiar with, that is the main part of our business. LCD display is made up of various components, and there are various material suppliers, and JSR provides some of the materials. We are strong in supplying some of the components of the LCD. And some of those materials are associated with the functionality, associated with the lights of optics, and the final category is edge computing, such as for the mobile device materials. So specifically the cameras, the peripheral material for the cameras are embedded inside the mobile devices. So those are the optical photonic material that we do provide. So as you have heard and may you have received the impression that the JSR's materials, there are plethora of materials we provide that demonstrate the functionality with the reaction or exposure to optics or the lights. molecular design for the materials that is associated with the functionality expressed by the optics or the light is very difficult because tracing through the experiment of the molecular changes over the exposure to light is very difficult, and that is difficult to be predicted utilizing classical computer simulation. So this kind of the photonics material as developed through the experiences and insights, and the new molecules are generated, and one candidate to improve the efficiency and precision as the quantum computing technology. JSR is involved in the quantum computing, and we are often asked the question why JSR is interested so much in quantum computing. So this is the why question we often face. So why now? Why do we have to develop the quantum computing? Or why now we have to do so? As a specialty chemical company, the source of our competitiveness is to design new molecules. Better performing material are to be designed. That is the competitive strength. That is quite important. For that objective, classical computer performing quantum chemical computation is indispensable tool for molecular design. However, unfortunately, classical computer conducting quantum chemical computation has to rely upon approximation. Sometimes approximation works well, other times approximation does not work well. I'm involved in about a decade or so of quantum computing when I'm encountering new class of the molecular computation or new type of molecule. The methodology validation of the computation is very difficult, so we have to depend on the insights and experiences for the validity approximation. So we'd like to reduce our reliance upon the approximation. So quantum computing is the candidate to be able to perform the quantum chemistry computing in a very accurate manner. So the reason why we developed the quantum computing, because in order to enhance the level of accuracy of the chemical calculation associated with the material development. Why now? Why do we have to develop the quantum computing right away? I refer to the digital transformation as an example. Currently, we are faced with the massive capacity of the computing resources at our fingertip. However, in the chemical industry, are we good at making the full utilization of the classical computing resources that is readily available to us? Not quite, because there are no such many people who are good at having domain expertise and at the same time good at programming. We don't have such talents so much. And if you try to work with external partners do not have the understanding or the deep insight about what our company JSR is doing. And the data format has not been organized or designed in such a way to accelerate development through computing. Therefore, a similar phenomena may take place in the future development of quantum computing. Digital transformation was accompanied with bitter experiences, so it is not too early. So we have blessed with the opportunity to embark upon quantum computing right away. So in the past 6 years, what kind of the quantum computing activities we have been involved at JSR? The exposure of JSR to quantum computing, 2016 January, Research Frontier Institute, that is an open innovation consortium hosted by the IBM. Quantum computing rapid development was evident by our participation in this consortium, and we identified this as an important potential technology. 2018, March 2018, we made investment into Cambridge Quantum Computing, currently known as Quantinuum. We have learned a lot from brilliant researchers concerning quantum computing. The major event was, as Dr. Coates talked about, 2018. Starting May 2018, we participated as a corporate member to IBM Quantum Network Hub at Keio University. Myself served as the resident researcher at Keio University. I have been involved in classical quantum computation, but I do not have the background concerning quantum computing per se. Therefore, I thought partnering will be required. Therefore, we began the joint collaborative research with QNASUS, who is the co-sponsor of Q2B. So I'd like to talk about the joint research together with the Keio QNASUS afterwards. 2019 November, we joined the Quantum ICT Forum. This forum addresses not only the quantum computing, but also we can learn about the quantum sensing. 2020 Quantum Innovation Initiative Consortium led by Tokyo University. We joined that consortium last year. Q-Star, which is the activity mainly by the Japanese industry. We participated in Q-Star. And yesterday we made a press release. We have begun the joint research together with the Cambridge Quantum or the Continuum this past April. So what kind of research are we involved? First of all, together with the QNASUS, Osaka University, and to a certain extent, with the support of Tokyo University professors, left-hand side, JSR, QNASUS, the first research 2018, toward the end of 2018 up to 2019. At that time, quantum chemistry algorithm was expected to perform the not so significant computing or quantum computing. In terms of the classical the quantum computing, highly accurate computing should be conducted by the quantum computing, but not so essential segment of the computation could be done through the approximation. So we conducted this research. This figure indicates the gray line represents the exact solution. Blue line represents the methodology we have developed out of this research program. Yellow, green, and red. Those are the outcome of the methodology of the classical quantum chemical computation. So the classical computation cannot reproduce the exact solution, but the methodology we have come out of this program, we're able to reproduce the exact solution. So this is the result out of the simulator. So this is the, maybe it is still NISC in terms of the computation, the structure, but letting only the quantum computing that is suitable for the quantum computing, but this is a methodology that is employed by the QNASUS. Right-hand side indicates this was announced by QNASUS in the past. Periodic calculation, periodic material. So solid and similar units are concatenated one after the other. In the JSR, that is not so prevalent, but the classical computer technology can be mapped to quantum computing, and how much extra computation cost will be added, or how less computation cost will be subtracted. So this is the exploration. So in the solid computation, property value that is more important than energy is the band structure. With this research, quantum computer was utilized for the band structure, explore the band structure. So we have developed such algorithm out of such a research, working with QNASUS. Chemistry application. So we are exploring the development of algorithm for the specialty of the quantum chemical computation. Then working with Keio University and IBM, as was illustrated by Kochi-san at the first presentation, Keio University is involved in very broad range chemical molecule applied to the actual machines, what kind of outcome is achieved, what kind of error correction will be required. So I'd like to share with you, this is the research. This is much more fundamental research. 2018, on the Keio Q-Hub was inaugurated. We were involved in the variational quantum eigensolver, that is a computation methodology. VQE, the variational quantum eigensolver, was embedded with the challenges such as the classical solution do not converge, and the accurate outcome was not achieved. And parameterized quantum circuit that expresses the quantum circuits, how the embedment could be done to be able to express even initialize a NISC, but that was not elucidated. So there were a plethora of questions at the Keio Q-Hub variation quantum eigensolver or variation quantum algorithm in broad sense of the word. At the Keio, they are conducting various the researchers, parameter quantum circuits, expression capability to be enhanced. Left-hand side indicates the conventional methodology. This is U theta, described on this diagram. Theta, that's rotation angle. Usually try to optimize the rotation angle, but we tried to optimize the rotation axis, not the angle. So what was the advantage of this optimization of the axis? As this diagram indicates, outcome, the red line compared to the conventional classical methodology gives lower energy on the vertical, the horizontal axis. This is a layer number. So what is the depth of the quantum circuits? The number of layers, the shallower regions, the energy level is lower. So one circuit expression capability is enhanced. The left-hand side, the research indicates fixing the angles and axis are to be optimized. And the right-hand side, brilliant student by name Wada-san, who is in the M1 grade when he was in the 4th year of the undergraduate program. Simultaneous optimization of axis and rotation angle. So that is the equation this Wada-san has identified. So this is not VQE. This is not applied to VQE, but this was applied to chronological evolution. So the advantage is the axis and the angle optimized. So the 1 qubit, everything can be optimized. So at Keio University, not only the chemical area, but utilizing the variation quantum algorithm, the basic fundamental research is also focused by the Keio University research. Finally, what I have learned over the past 4 years. Let me share with you what I have learned. Quantum computing technology is advancing steadily. 2018, I joined Q-Hub. I touched quantum computer. That was not quite useful, honestly speaking, but in the 3 years after that, there was a great leap forward in advancement. The advancement was much quicker than what I had anticipated. Not only the superconducting or other tracks you may have heard, photonics, and new devices are emerging. The technologies themselves are making great advancement. What I have also learned that Koki-san talked about quantum AI and reservoir calculation. Quantum chemistry alone may not have so many use cases. Quantum AI, quantum optimization, or quantum reservoir applications. So those are the applications. Leading edge the research areas, so we explore it to identify the use case. So this is quite important, try to identify the use case. So it's not just the quantum computing. Dr. Yang was talking at the opening, but sensing or the communication or quantum materials. For the industry, those areas may have great impact. So we should closely monitor advancement in those areas. Finally, what we need to take home out of this experience, I have listed this on the slide. Thank you very much.